Assalamualaikum warahmatullahi wabarakatuh and very good morning. We are from Group Inas and my group consists of Akila, Liminyan, Karunisa, Vishnu and Nushafika Amira.
For this assignment, we need to choose a heterogeneous catalyst used for trans-esterification reaction for biodiesel production. So there are four parts in our presentation, which is first current catalyst, which is calcium oxide. Second, the improved catalyst, which is calcium oxide supported by silica. Third is catalytic reaction for biodiesel production, and last one is comparison between calcium oxide and calcium oxide silica. So next, I will pass the presentation to Amira.
Properties of calcium oxide. Calcium oxide is usually made by thermal decomposition of minerals such as limestone and natural sources such as seashells and eggshells which contain calcium carbonate. It is cost-effective, highly available, non-toxic and easy to prepare. It also has a low surface area but high basicity value. High basicity will enable calcium oxide to have a good activity on the all-trans esterification reaction to biodiesel. Although it shows high catalytic activity, the calcium ion will easily leach away from the solid catalyst during the reaction. There are two ways to synthesize calcium oxide. First method is thermal decomposition, which is an endothermic reaction because it requires heat to break down a chemical bond into a simpler compound. Decomposition of calcium carbonate will produce calcium oxide and carbon dioxide. However, different raw materials require different temperatures of calcination to obtain calcium oxide. Second method is co-precipitation. It is commonly used to obtain a material with small particle sizes such as nanometers. Calcium oxide is obtained through repeated dissolution and precipitation. The co-precipitation method is also used for synthesis of catalysts with higher basicity. Procedure of thermal decomposition. Firstly, the shells will be rinsed with water to remove any impurities and will be dried in an oven. Then, the dried shells are calcined at 700 to 1000 degrees Celsius in air atmosphere. Next, the product will be crushed and sieved. Lastly, the product will be obtained as white powder. Please take note that all calcined samples must be kept in a closed vessel to avoid the reaction with carbon dioxide and humidity in air before being used.
Now, let's look at the improved heterogeneous catalyst by introducing silica as a support. This supported catalyst is synthesized by wet impregnation method. First, 5 grams of calcium oxide is added to 100 ml water. Next, the aqueous solution is added to 3 weight percent amount of silica and mixed vigorously under reflux for 4 hours at 80 degrees Celsius. Then, the impregnated precursor is filtered out and dried in an oven. The dry mass is then calcined to activate the catalyst in a furnace at temperature of 80 Celsius for 3 hours before further characterization. As for its properties, apart from its low cost, the catalyst provide high biodiesel yield up to 90% due to the increment of surface area, which provide more active sites, and 20% silica content is sufficient, and excess silica is not needed since it will inhibit the kinetics of trans-esterification reaction. Second, it provide high surface area where BET surface area of the supported catalyst is larger. Hence, this improve the catalyst activity by increasing the accessibility of the active site and provide enough attachment area. Besides, it has a larger average pore diameter, so the reactant molecules can easily attach to catalyst and most of the active site will be utilized. Third, it has large pore size where it has a bimodal pore, so it increases the diffusion rates of reactants on the catalyst surface, product selectivity and catalytic activity. Fourth, it can restrain from sintering and calcium leaching. From the SEM image, supported catalyst has smaller aggregates and less sintered, which means it enhances the surface area for the catalytic activity with a larger area of dispersion. The supported catalyst can form calcium-oxygen silicon bond that can prevent the leaching of calcium ions and unnecessary reaction with reactants. Lastly, it can be reused by 8 successive run and shorter reaction time. It is a simple and sustainable method as it can reduce the energy consumption.
Thanks Karunisha for the presenting. Now let us move into the catalytic reaction. Waste cooking oil is one of the best oil sources for making biodiesel, but due to its high free fatty acid content, converting waste cooking oil to biodiesel while the trans-esterification process would bring a lot of issues. To alleviate the issues, pre-treatment with an acid catalyst prior to trans-esterification is proposed. First is the esterification of the free fatty acid with hydrochloric acid and methanol, followed by the trans-esterification of the pre-treated product with an alkaline catalyst. In the presence of hydrochloric acid catalyst, free fatty acid reacts with methanol to create ester and water, as shown on the next slide. Here is the equation related to esterification and trans-esterification process. In this slide shows the schematic diagram of biodiesel production, which generally undergo two processes. The feedstock used is waste cooking oil, and continuous stir tank reactor (CSTR) is used for simultaneous reactions of esterification of free fatty acid and trans-esterification of triglycerides. In the first esterification process, waste cooking oil stream with flow rate of 985 kg per hour is considered as a mixture of triolene and oleic acid. The composition is 50 weighted percent each. At the same time, the solid catalyst is continuously fed into the CSTR with a rate of 4.9 kg per hour. The residence time in CSTR is fixed at 2 hours since the reaction reached its steady state at around 100 to 120 minutes. The fresh methanol is mixed with recycled methanol in a mixture to form the mixed methanol stream. The waste cooking oil stream is then mixed with the mixed methanol stream and fed to the first CSTR, which is the esterification reactor by a pump at high pressure. The esterification reaction was carried out between 80 and 90 degrees Celsius at 1 atmospheric pressure. Products from the esterification reactor were cooled to 65 degrees Celsius and catalyzed were removed or neutralized before allowing into the setting tank to remove the methanol and water mixture. Lastly, the bottom product of the separating washer is taken to process 2 for trans-esterification reaction. The reactor stream from the esterification process are taken into a glycerol removal step before entering a second CSTR, which is the trans-esterification reaction column, along with catalyst and alcohol mixture. Reactor temperature is usually maintained at 65 degrees Celsius and 1 atmospheric pressure and 1 to 6 molar ratio of oil to alcohol. Next, the products of trans-esterification reactor are fed into separator 2. From the separation tank, biodiesel and alcohol mixture is distilled to separate methanol and biodiesel. Biodiesel is then washed with hot water and sent to a separator to remove water and biodiesel. From the third separator tank, biodiesel is sent to the storage tank. The methanol in alcohol and a glycerol distillation column was recycled and used.
Let's look at the comparison between silica-supported calcium oxide and unsupported calcium oxide. The first comparison is about the reusability. Silica-supported calcium oxide can be recycled for 8 successive runs, and it can be used through the next 3 consecutive runs where the yield is still more than 90%, while the unsupported calcium oxide can only be used 4 times. When we compare the surface area, silica-supported calcium oxide has higher surface area, which make more active sites. When the number of active sites increases, the potential energy barrier in reaction path decreases. Thus, this will produce higher yield. While the surface area of unsupported calcium oxide is lower, it is not capable of dispersing good metal oxide to increase the catalytically active surface, and it lowers the yield. Furthermore, regarding the tolerance of water and free fatty acid content, the acidic nature of silica makes it suitable for esterification of fatty acids. It is also capable of achieving high yield regardless of water content. Silica-supported calcium oxide is identified as acid-base catalyst, which improve esterification and trans-esterification. While for unsupported calcium oxide, it is less active in oils with high free fatty acid values. So the rate of reaction decreases drastically when there is water content.
So with that, it's nearing to our end of our presentation. Here is the job description for each one of us, and here is the reference that we use for our presentation. So with that, thank you and have a good day and stay